Hello and welcome. This is section 2.3 and we're going to talk about limit laws. So in the previous section we talked about the idea of a limit when we were looking at a graph and what that means, and today we're going to start doing some algebra to calculate limits. So I'm going to go through the limit laws kind of quickly. You can find these in your book at the beginning of section 2-3. The first limit law is that if you take the limit as x goes to a of x, and that's going to be a, and we're going to say that for these laws, a and c, which we will use, are going to be constants, real numbers. Okay, so for example, if I take the limit as x goes to 2 of x, well, your first rule is try plugging in the number. So if I plug in 2 in for x, I get 2. That's basically what it's saying. So it's not a big surprise, but we want to be thorough in our definitions. This one's also fairly obvious. If you take the limit as x goes to a number of a constant, then there's no x to plug in for. That limit is just the constant. Okay, the next few laws have to do with operations. So I'm going to combine the sum and difference rules. They are the same. If you take the limit of two different functions and they are either added or subtracted, I'm going to stack those, then that's the same as taking the limit of the first function and then adding or subtracting, as the case may be, the limit of the second one. So the way I think of this is it's kind of saying that the limit distributes over addition. You can hop that in and take the limit of each part of a function if they're added or subtracted. Okay, the next rule is for multiplication, and it's very similar. If you have two functions multiplied together, then that limit will distribute in, and you can take the limit of the first thing times the limit of the second thing. Alright, and then division, same. So basically the limit distributes over all operations. That's what we're saying here. Alright, those are your division rules. There's also a power rule. We'll call that 6. If you're taking the limit of a function and the whole thing is to a power, you can take the limit of the inside function and then raise that answer to the power. So basically you can power out your function and then plug in your number, or you can plug in your number and then power out the function. The order doesn't matter there. And the last one, there's some restrictions on this. If you have a root, then the root can go, you can take the limit of the function and then take the root. Now this is if n is odd, then this works for all values. Okay, because an odd root doesn't care if the stuff inside is positive or negative. You can cube root a positive 8 and you can cube root a negative 8. So for odd roots, it's all good. But if n is even, so if we're taking a square root or a fourth root, then we know that this part inside can't be negative. So this is going to be only if this limit turns out to be greater than or equal to 0 or positive. Okay, so basically everything's legal, except if you're dealing with roots, you got to make sure that you're not rooting a negative, even rooting a negative. That's what it kind of boils down to. All right, so now let's get into the nuts and bolts. How do we calculate limits? Okay, I'm going to give you a list of what to do. The first thing that you do when you have a limit is you always try to plug in the number that you're taking the limit to. So in our examples, that would be our a value. So whatever you're taking the limit as x goes to, you always try to plug that number into the function, because sometimes that works, and if it works, you're done. Okay? Oftentimes it doesn't, and something bad happens. So if something bad happens when you plug in the number, like you get 0 on the denominator or something like that, then here's what else you can try. You can factor and cancel, and you could add fractions, or you can multiply by the conjugate. I don't know if you remember in pre-calculus, but when we were proving trig identities, this list is very similar to that. Basically, you're trying to do the same thing. When we were proving trig identities, we were trying to just manipulate one side of that equation to make it look differently, to make it look the same as the other side. So we're just trying to shift how it looks around, and that's the idea with a limit. I want to do a little bit of algebra and see if I can make it look differently so I can get that 0 off the denominator or whatever bad is happening. And so these ideas of what you can try are the similar ideas to those proofs, so you'll start to see some patterns. Obviously, if you are going to factor and cancel, that's going to happen when you have polynomials. If you're going to add fractions, well, you better have fractions. Okay, so that's how you know what to choose. And then the conjugate is always associated with roots. Whenever you have a limit problem with a root, the first thing I think of is conjugate. All right, so let's do some examples. I'll try to do an example of each type, okay? And I'll give you a problem in the book to try on your own after I do each example. So first one is limit as x goes to 6. Okay, those of you who have had me before will know that arithmetic is not my strong suit. So I'm rarely going to make a mistake on calculus, but I often make a mistake multiplying things out. So check me and make sure that I'm doing it right. This is the downside of doing recorded lectures is I can't have somebody raise their hand and go, hey, 2 times 3 is 6, not 5. So make sure that you're checking my arithmetic. I will try really hard not to make a mistake. Okay, so the first thing is we're going to try to plug numbers in. That's the first thing that we're going to do on every problem, because if it works, great, we're done. So the first thing I'm going to do is plug in 6 everywhere I see x and crank that number out. So this is going to be 12 minus 1 is 11, and this is 6 plus 4 is 10, square root of 10, and that's fine. You can reduce the root if you want. This one doesn't happen to do that. I do not want decimals. Okay, just this is great. 11 root 10, that's your answer. So if you get any kind of like real number answer, that you're done. That is the limit. Okay, so that's an example of the first type of problem. Let's look at another one. We are going to do limit as x goes to -3. All right, so we're going to plug this in. We're going to plug in -3, and very quickly, I always do the denominator first to just check, because that's often where things are going to go wrong. You're going to get 9 minus 9, which is 0 on the bottom. So sad. Okay, so we need to do something. I look at this and I say, okay, I've got polynomials. So probably what I'm going to do on my list is factor and cancel. So let's try that. And it's possible that you try something, it doesn't work, so you go back to your list and try something else. So the top of this guy factors as x plus 3, x plus 1, okay, multiplies to give me 3, adds to give me 4, and then the bottom is the difference of 2 squares. And look at us, okay, we've got these guys are canceling, so that's going to give me the limit. I need you to write the limit every time, every step. I will mark off points if you drop the limit. The only time you're allowed to drop the limit, and when you need to drop the limit, is when you plug in the number. So now at this step, once I cancel a factor, I'm going to now plug in this -3 in for all my x values. And when I do that, that is me taking the limit. So now I don't write the limit anymore. Okay, I just have the numbers, -3 minus 3, and that's going to give me a -2 on top and a -6, which is a positive 1/3. Okay, so that's what factoring and canceling looks like. Let's do this next one. This next one's, oh, just kidding. I'm going to not do that. Oh, no, that's fine. That's fine. We'll do the adding fractions next. Okay, my examples were in different orders. Let's go, the limit as x goes to -3 of 1 over x plus 2 plus 1 over x plus 3. Oh, back up. I want you to, this is a great way to study. Once you do see this problem that I did, the factoring one, now you could go into your book and you could try example 2.17. Now, this example is worked out for you. It's very similar to the one I just did, some different numbers. So what you do is you go into your book to try one. You should pause the video and you should go try one on your own, okay? You cover the work so you can't see what they did. You look at the example, you write it down on a piece of paper and try it. Okay, so pause that and then come back. Okay, now that you've done that, let's check this guy out. First thing I do is plug in this value, and I always start on the bottom. Oh, look, -3 plus 3. That's going to give me 0 on the bottom. Sad face. All right, so that means I need to do something. I'm looking at a whole lot of fractions. So my plan is to add fractions, and if you remember, we did a lot of these in pre-calculus. Hopefully you did if you did not have me. And the trick is you need to get the top to be 1 fraction and then the bottom to be 1 fraction. Now the bottom's already a fraction, and so this is its own guy, x plus 3 over 1 in fraction land. The top, though, I need to combine these. So in order to do that, I need a common denominator. So I'm going to multiply by x plus 2 here, and that's going to give me 1 over x plus 2 plus x plus 2 over x plus 2. I am showing you all the gory details. If you are cool with the algebra and want to skip a step here, that's fine, as long as I can follow what's happening. All right, so now we're going to add the tops. The way we add fractions is top. So I've got an x on top, and then I've got a 1 plus a 2 up here is going to be a 3 over my common denominator all over x plus 3 over 1. Once you have the fractions, 1 fraction over 1 fraction, you flip the bottom and bring it up. That is going to be, I mean, we did that, I don't know, 5 million times in pre-calc. And then look what happens. This up top, this x plus 3 and this x plus 3 cancel. So the only thing that I'm left with is 1 over x plus 2. The 1's got to hold the place on the top, and the x plus 2, and everything down here canceled. So I've just changed the form of this. I haven't changed the value at all because everything was legal in algebra land. Now I'm going to try to plug in again, and hopefully I don't get 0 on the bottom. So I'm going to take, let's mark this out. You're going to take -3, plug it in here for x, okay? So, and I'm dropping the limit sign now because I'm plugging in the number. So this is going to be 1 over -1, which is -1. All right, that's what adding the fractions looks like. Now, what you want to do is stop the video, and you want to go do example 2.18 in the book. Okay, again, no, that's not right. I'm out of order, sorry. 2.19 in the book. So again, look at that problem. Don't look at what they're doing. Cover it with a piece of paper, write it down, and try to work through that, and then check your work. Okay, that's what if we were in class in person, that's what I'd be having you do right now, is try a problem on your own. All right, so go do that. And next we're going to do conjugates. Oh, we're going to make that x -1, -2. That -2 up top is not under the root. Okay, so going back to our list, this is this last one, multiply by conjugate. That's our last kind of trick in the bag, so to speak. So again, I start by trying to plug in 5, and I can see that that's not going to work. I'm going to have 5 minus 5 on the bottom, 0, bad. Okay, so what do? We're going to take this, over 0, sad face. So we are going to take this and multiply by the conjugate. What the conjugate is you take wherever the root is. Now the root can be on the top or the bottom. It does not matter. In this case, it's on the top. And you multiply by that whole top or bottom, wherever the root is. Okay, but you change the sign in the middle of the two terms. You do not, just kidding, there's a typo. Sorry, this should be a 1. You do not change the sign under the root. Okay? Say that to yourself. I will not change the sign under the root. You only change the sign in the middle of the root and the number that's hanging out by itself. Okay? If there's only a root, then you just multiply by the root. You don't change any signs. Okay? But if there's two terms, you change the sign in the middle. And because algebra land says we have to keep everything even, you do the same thing on the bottom. So we're really multiplying by this over this, which is 1. We're not changing the value at all. All right, now algebra strikes again. Let's talk about multiplying polynomials. Remember foiling, because this is a 2-term by a 2-term on the top. So I'm going to write this over here. Limit as x goes to 5. I'm going to first multiply these first 2 terms. And I'm going to write this out the first time, but I'm probably never going to write this out again. Okay, I just want to make sure I don't lose anybody. It's root x minus 1 times root x minus 1. That's root x minus 1 squared. Okay, that's what the first 2 terms are. The next thing we're going to do is we're going to multiply the outside 2 terms. So that's going to be a 2 times this root. So I've got a positive 2 times the square root of x minus 1. The next thing we're going to do is multiply the inside 2 terms. And by the way, the order I'm doing these in doesn't matter. You can do any order as long as you get them all. I've got a negative 2 times the root. And then the last thing that I'm going to do is multiply the last 2 terms. That's a negative 2 times a positive 2 is a negative 4. Okay, that's all 4 terms in the top. Now, what's happening in the bottom? It's just these 2 terms. Here's my rule. I don't ever multiply out denominators until I know that it's going to be beneficial, because when I write my denominator like this, it's factored, which means that if I want to cancel something with the top, I'm ready to go. If I multiply it out, then I'm going to have to refactor later. Okay, so save yourself some time. Denominators don't typically multiply out. Now let's clean this up a little bit. Look what happens. First of all, the squared and the square root cancel. Okay, so I'm left on the top with just an x minus 1. The other thing that happens is these middle two terms cancel. You've got a plus 2 root and a minus 2 root. That always happens with the conjugate. That's why we change the sign, so that those middle two terms cancel. And then the last term I'm left with is a minus 4. So look at how well that cleaned up. So this is going to be x minus 5. Oh my gosh, magic's going to happen, because look at what happens. This factor cancels with that factor. All right, so I'm left with 1 over just this part of the denominator. And now I've changed how it looks, and I can try to plug in the number again. So I'm going to take 5, I'm going to plug it in here and see, and hopefully I don't get 0 in the denominator again. So I'm dropping the limit sign. This is going to be 5 minus 1 plus 3. So this is the square root of 4, which is 2, which gives us 1/5. And that's the answer. All right, so those are the main algebra tools for evaluating limits. Oh, if you want to pause and try one of these on your own, let's see, you can do example 2.18 right now. Just stop the video, go do that, and make sure you get some of these under your belt before we move on. Okay, special cases. Let's talk about the first special case I want to mention is if you have left or right limits. Okay, so that would be like, say, the limit as x goes to 3 from the right of something like this. So this is what I'm talking about with the left and right limits. If you've got a plus or a minus right there, then I usually draw the picture and do it like we did in the last section. You just do it like looking at a graph. So for example, with this problem, I would say, okay, this is a square root function. I remember those from pre-calc. They generally look like this, but this right here shifts it right 3. So 1, 2, 3 to the right, and it's going like that. Okay, so that means that I want to come into this limit right here at 3. And we talked about the way you know if the limit exists is if the limit on the left equals the limit on the right. So in this case, there's no left side of this. It's undefined. So the limit doesn't exist, so we can only talk about the right-hand limit. So here's what that means. I am marching in from the right-hand side, and the question is, as I get close to x equals 3, what is my y value getting close to? And the answer is 0. Okay, so if you get right or left hand limits, don't try to do algebra on those, and I would just draw a picture and write down the answer. The second kind of special case for me is piecewise functions. And my strategy, basically my strategy is this. If the algebra doesn't fall out like one of those first three examples, graph it. If it looks anything weird, graph it. If I get anything with absolute values, I graph it. Absolute values freak me out. There's all sorts of weird things that happen with them. Piecewise functions, who knows what's happening. It's worth a draw. Okay? So this is why we spent so much time graphing in pre-calculus. All right, here we go. If you were in my class, the way I taught you how to do piecewise functions is graph all three of these independently. So first one's going to be in red. It's a line, y-intercept of -2, slope of -1, looks kind of like this. Okay, outline. Next thing I'm going to do in green, that's just y equals 2. That is a horizontal line at 2. Okay, and the last one we'll do in blue. That's x cubed. Looks like this and this. Try to be exact with these, okay, because we like to see where they're going to intersect. Right, then you look at the dividing marker. Let's do this in orange. The divider marker is -1. That's an x value. So I like to draw this little thing. It's not an asymptote, but it just helps me see where I'm splitting my graph at -1. So what this says is, now I'm going to draw the real graph in black. When x is less than -1, I want to be on the red graph. So less than is to the left. So I'm going to say this right here turns black. That's the real part of the graph. And I erase the rest of the graph, the other part of the graph. Okay? I'm going to have to get in here and do that little part. There. Okay? So I only have that black part of the line to the left. Now what happens is when x is equal to -1, I want to be on the green graph. So on this vertical orange line, I'm going to put a dot right here. Okay? Because that's the green graph and the rest of the green graph goes away. And then when x is bigger than -1, I want to be on the blue graph. So that means I want to be on the blue graph going to the right. The right is bigger. This direction is positive infinity. This direction is negative infinity. Big, small. Okay, and I erase the rest of the blue graph. There. Okay, and that's the picture of my graph. And then if you, this orange part is not technically part of the graph. You can erase that as well. It doesn't really matter for our purposes, but just don't start thinking it's an asymptote. So this place right here is an open hole. The graph comes into that open hole and then does its cubic out to the right from there. So now that you've got the graph drawn, I want to know what is the limit as x goes to -1 from the left. Okay, so that means I'm going to jump on my graph on the left, which is over here, and I'm going to come in towards x equals -1. And as I get close to x equals -1, what is my y value? Remember, a limit is always asking for a y value. And you can see that that is going to be -1. That's your answer. Now, some people are super cool and they can see this picture in their head without drawing it. If that's you, by all means, please do that. But I am not cool like that and I can't do that. So, all right. And then the last special case that we're going to do is when your limit comes out to be in the form of c over 0 for c not equal to 0. So all the other examples that we did, when we plugged in the number, we got 0 over 0. I didn't go through all those details, but you can go back and look at that. They all turned out to be 0 over 0. But sometimes what happens is when you plug in the number, so again, that's how we always start, is plugging in the number here and here, I don't get 0 over 0. I get 3 over 0. So it's a number up top and a 0 down below. These problems are a little bit different. These are not your typical problems, and I'm going to show you one technique for dealing with these. And what we're going to do is we're going to split this fraction apart into two pieces, the top and the bottom, because we want to look at what's happening at the top and the bottom independently. So this is going to become the limit of x plus 2 times the limit as x goes to 1 of 1 over x minus squared. Okay, now convince yourself that that's the same thing. If you multiplied those two together, so let's just over here on the side, if you took x plus 2 over 1 in fraction land, multiplied by 1 over x minus 1 squared, that's what this would be. They just multiply straight across, you'd get back where you started. So all we're doing is just pulling it apart, top and bottom, and then we are going to evaluate each of these independently. So this is going to tell me what's happening with the top. Okay, plug in the 1. So this is 1 plus 2, which is 3. Okay, and then what's happening here? When you plug in 1, and you get 0 on the denominator, let's take a look at what that graph looks like. Okay, because graphing is always a really great strategy for evaluating limits. Let's go in here, let's type in our 1 over x minus 1 squared. Alright, so this is what it looks like. And it was asking for the limit as x goes to 1. So look at what happens. Oh, I just tried to write on it. I can't write on it. But look at where 1 is on the x-axis, and what happens to the orange line. It shoots straight up, right? So what's happening is that fraction it's going to infinity. The limit is infinity. Okay, so let's go back over and draw a picture of that. Here's what we found this looks like. It's generally, oops, it's not that far over. It's got an asymptote at 1, and it's doing this, right? So at 1, the function is shooting up towards infinity. Now, how can we see that algebraically? Well, I've got, when I plug this 1 in, instead of plugging 1, plug in 0.9, all right? 0.9 minus 1 is negative 0.1. You're going to square that. It's a really small number. If you divide any number, whole number like 1, divided by a small number, you get a really big number. Okay? Whole numbers over decimals are really big numbers. So that's shooting up to infinity. All right? And 3 times a big number. Does a big number care that I'm being multiplied by 3? It's still a big number. So this limit is infinity. But the idea is that you want to take it out of division and you want to turn it into multiplication so we can be clear. Division's a little tricky because if the top's big and the bottom's big, how much bigger, because division kind of cancels off of each other, but multiplication is clearer. It's like, okay, a big number times a big number is a big number, always. So you're trying to change it from division into multiplication. That's the idea there. There aren't very many of those, but you can play around with that. And let's see if there's anything else we're going to do. Okay, two more special limits that I just want to show you. This is something to memorize. If you are interested in why this is true, the proofs are in the book. I'm not just for length of time. These videos are long anyways. I'm not going to go through that, but they're in the book if you're interested. They are kind of interesting, and we can talk about them in class if you want. But for the meantime, I want you to memorize these, okay? The limit as x goes to 0 of sine x over x is 1. And the limit as x goes to 0 of cosine x minus 1 over x is 0. These are really common limits that come up, and their answers are not immediately obvious. And so they are, in my opinion, best just inserted in your files somewhere to use along the way. You will use those all the way through Calc 2 and 3. Okay, that's it for now. So you can try the homework for section 2-3, and we will talk and answer questions in class. Good luck. See you then.